2025, I guess there was a bit of a chaos in the government, and NASA was no exception. Um, but I was able to put together some things that may be of interest to you. As you can see from the agenda, I have a lot of things on there. Some of them are kind of small, but important. And at the end, I have a wrap up video that I don't want to scare anybody, but it's 3 hours long. And
Good.
but I will only do the first 30 minutes of it, and the rest of it you guys can do on your own because the instructions will be there. It's quite interesting. It basically is a video that says what do we know and what we don't know. Okay,
Right. No spoilers.
so that's an important thing. Uh, okay, so let's get started. NASA organization. We finally got a administrator, Jared Isaacman, who was the nominee almost a year ago, or like 9 months ago. He was one of Elon Musk's guys, and then when the fallout occurred between Musk and Trump, Jared was pulled, and so NASA became kind of a bouncing ball between the various people that Trump nominated for his cabinet. And I guess the guy who took over was the minister or secretary of transportation, but he didn't really care for NASA. So, things kind of chugged along. Fortunately, when I look at the fallout, and I have a recent copy of Science magazine. Out of 2,000 some people at NASA, only 157 departed. So compared to the other organizations, it's actually pretty low. But the Jared has a leadership direction. He's an astronaut, although he has no technical background, but he has flown in space, and he's quite interested in human exploration. And so he kind of has three directions that he's announced: sustaining American leadership in human space exploration. Notice the human space exploration. He doesn't say space exploration. So I don't know what that means is robots are out and leaders, humans are in. But anyway, that's what he said. And then he says accelerating exploration timelines, which is very important if you think about it, because sometimes NASA does things very, very slow. It's safety oriented, but it's very, very slow. So he's going to push it. And then he wants to emphasize competitive global space endeavors. And this is good. He says, we're going to look at the rivals. So that means that the Chinese or the Russians probably are no longer in the space race. But anyway, he's competing. So that's good. Uh, now, global launch activity, we had a large number of launches last year. Many of them were associated with Starlink, because if you remember, Starlink wants to have thousands of satellites, and so they're putting them up like every month or two, or several of them. But then there are other launches, China and commercial. Now, here's a video that kind of shows the advancements that we made in reusable rockets, which is important because you can't have many space launches uh, without having some kind of a reusable system. So here is a short video on that. Okay.
Reusable rockets are revolutionizing spaceflight. The movement may have begun with SpaceX and their Falcon 9, but it's quickly spreading across the world. Chinese rockets are landing themselves right now, just not always successfully. Blue Origin is figuring out how to land their own gigantic rocket booster, and an underdog startup out of New Zealand is looking to join the game this year with a reusable rocket of their own. For all of the many differences between these vehicles and their builders, there are fundamentals that tie them all together, the key ingredients of the reusable rocket, and this is what makes them work. To begin, we should clarify that when we say reusable rocket, what we really mean is the booster stage. Typically, that's the lower 2/3 of the fully stacked rocket. A booster is essentially just a big fuel tank with some engines at the bottom. At this moment, there is only one rocket booster in the world that has proven to be consistently reusable, and that is the SpaceX Falcon 9. So we are going to use this as our reference point, but the same process will apply to all of the new rocket designs that are in development. Now, you might also be familiar with some reusable upper stage vehicles, also known as orbiters. The Space Shuttle is a famous example. The SpaceX Starship is a more modern example, and there have been a few reusable spaceplanes developed in between. These orbiters are significantly more complex and diverse vehicles, each deserving their own explanation, so we're going to put that subject to the side for today and keep our focus on the reusable rocket booster. While the Space Shuttle may have been famous for its orbiter, this 1980s-era NASA rocket also pioneered a method for reusable boosters as well. If we look at how the Space Shuttle was configured on the launch pad, we have this big orange tank in the middle that holds liquid propellant for the main engines. On the backside is the spaceplane, and to the right and left are the side boosters. These burn solid propellant, just like a model rocket engine, and their job is to get the shuttle off the ground and through the most dense section of Earth's lower atmosphere. At an altitude of about 45 kilometers, or around 4 times the height of a commercial airplane, the side boosters are released and allowed to fall back down to Earth. The reason for this is you don't want your orbiter to carry around any dead weight, so once the booster's job is done, we always separate the stages of our rocket. Now, this is where most conventional rocket boosters will simply fall back down into the ocean. American space launches typically lift off from the east coast of Florida, so by the time stage separation occurs, the rocket is far out over the Atlantic Ocean. If you were to dive down to the bottom, you'd find an enormous graveyard with hundreds of old boosters scattered across thousands of acres of seabed. This is not an ideal way to operate. It's bad for nature, but it's also bad for us human beings too. We've taken months or even years worth of highly complex engineering work and expensive materials, and then we've converted that all into a pile of garbage at the bottom of the ocean that only ever contributed about 90 seconds of actual usefulness. Now, wasted time and resources is one thing, but it's the wasted money that has really driven the movement towards reusable rocket technology. Every time you watch a conventional rocket booster fall helplessly back to Earth, that's somewhere in the neighborhood of $50 million sinking down to the bottom of the ocean. Something that you won't find in the rocket graveyard are side boosters from the Space Shuttle, because after stage separation, these rockets actually deployed parachutes and floated softly back down to the water, where they'd wait for a boat to arrive and tow them back to port. Once all of the solid propellant is burned up, you're essentially just left with 2 empty metal tubes. Now they just need to be cleaned up and refueled before they're good to go for another shuttle launch. And for many years, that was the only way to reuse a rocket, until SpaceX came along. Falcon 9 introduced a new concept to the world of rocketry: vertical takeoff and vertical landing. That means we are not just parachuting our way down into the water anymore. The booster will guide itself back to the landing pad for a controlled descent, which begs a question. Why didn't SpaceX just go with the parachute method? Sounds a lot easier, right? And it is, but there's an important distinction to make. On the space shuttle, all of the important and delicate flight hardware was inside the orbiter, which landed itself on the ground. It didn't get wet. Now, on a conventional rocket that doesn't have a spaceplane attached to it, all of that flight hardware is located inside the booster, so you don't want to get water in there. But since you already have all of those computers and electronics on board that guide the booster off the ground and into space, you could theoretically use that same hardware to just run the play in reverse, guide it from space back down to the ground. The idea wasn't unique to SpaceX. Rocket scientists had been pondering this method for decades, but it was always written off as being simply impossible to accomplish in the real world. The New Zealand startup Rocket Lab actually tried to cheat the system with their Electron booster. What they had planned to do was parachute the rocket down through the sky, and then just before it hit the water, a helicopter would fly in and snatch it out of the air. That was a badass plan, but when they actually tried to do it in real life, the helicopter pilot quickly realized this was way too sketchy to be safe, and he bailed on the catch attempt at the last minute, and the company never tried it again. Anyway, back to our timeline here. In 2011, SpaceX would begin their quest to achieve the impossible. By 2012, they began flying a test vehicle called the Grasshopper, a small fuel tank with a single engine and 4 fixed landing legs. It was designed to fly up about 1 kilometer and then come straight back down for a vertical landing. This kind of maneuver is often referred to as a hop. Grasshopper experienced some trial and error, but it was able to accomplish 8 successful hops in 1 year of operation. What this test demonstrated was our first necessary ingredient for a reusable rocket, an engine that can be throttled down to a very low power level. In order to land, you need the engine to burn just enough to slow you down, but not so much that it starts to push the rocket back up again. This is a delicate balance, and that's exactly what SpaceX was trying to find with Grasshopper. In 2013, they began scaling this test up to the Falcon 9. That name tells us that this rocket has 9 engines, which is a lot. Most rockets previous to this had 4 or 5 engines at most, but SpaceX knew that they wanted a reusable rocket booster, so instead of using a small number of big engines, they chose a large number of small engines. This is essential for achieving that balance we talked about earlier. By the time our rocket comes in for a landing, almost all of the fuel in the tank has been burned away, so it's mostly just a big empty tube, nowhere near as heavy as it was during launch, so we only need a little bit of power to slow it down. A big engine, even running at its lowest power level, is still going to push too hard, and that would actually keep our rocket in the air. It wouldn't be able to touch the ground. That is what we saw in Phase 1 of Falcon 9's experimental landing program from 2013 to 2015. The rocket would fall back from space, over the open ocean, and it would relight that one center engine to slow down for a very soft landing on the surface of the water. That was the first real-world test, and what SpaceX was trying to prove was the ability to restart their booster engines mid-flight. This was not something that any other rocket maker had really needed to consider. You light your booster on the launch pad, you burn until it runs out of gas, and then it winds up as another addition to the rocket graveyard. But in order to land your booster, it actually needs to stop and restart the engines multiple times on the way back down. This is where problems tend to arise. Rocket engines are volatile by nature. When you light them on the launch pad, you do so in the ideal condition. But when you try and do the same thing in mid-air, stuff tends to explode. Check out the second test flight of the SpaceX Starship. The booster was going to attempt a soft water landing, just like what we saw with Falcon 9. But as soon as it tried to restart those engines to begin slowing down, boom. Unfortunately, this is the kind of thing that you can only test by doing it live. So as more and more reusable rockets join the party, we're probably going to see a nice variety of mid-air explosions. It's all part of the process. Now, we know that reusable rockets need small engines to land, but they also need a large amount of power to lift off. For a rocket to achieve reusability, it's actually going to need more power than a conventional rocket just to get the same amount of mass into space, and that's why you'll typically see a big cluster of those smaller engines all tied together. We have to remember that a disposable rocket booster is free to burn all of its fuel on the way to space, because it's just going to fall back down and splash into the ocean. But a reusable rocket needs to fly all the way to space, reaching a top speed of around 8,000 kilometers per hour, and then it needs to slow all the way back down again to reach a speed of 0 at the moment it touches the landing pad. That requires a bunch more fuel to be held in reserve for the landing. We also have to consider that a reusable rocket is going to be heavier than a disposable equivalent because there's a bunch of extra hardware that is necessary for landing but needs to be carried all the way into space before it really gets used. Most of that excess hardware is going to be needed to help steer the rocket because going up only requires a very minimal amount of guidance, but getting back down is where the real magic trick begins. Following stage separation at an altitude of around 80 kilometers, our rocket booster is going to begin the process of slowing down for a return to the launch site. In order to do that, we have to flip the entire rocket around so that the engines are pointing in the opposite direction. On Falcon 9, this is done using cold gas thrusters, which are little jets of compressed nitrogen gas. Thrusters are located in 2 pods on opposite sides of the rocket, right near the very top. This position gives them the maximum amount of leverage to push the booster all the way over and get the top end pointing back at the ground. Now we need to fire up all 9 rocket engines to start canceling out all of the momentum that we just built up by flying to space. This is called the boost back burn. It's going to change our flight path from a big arc that goes out over the ocean to a loop that brings us back down to where we started from. Once the rocket is going slow enough that it starts to fall back down to Earth, we actually need to flip around again and get the bottom pointing back toward the Earth. As we begin to hit the atmosphere, a lot of heat and pressure is going to start building up underneath the rocket, and the best way to relieve that is actually to fire up the engines yet again. The re-entry burn will slow down the velocity even more and relieve some of that pressure. But the exhaust from the engines will actually push a lot of that excess heat away from the rocket and create a sort of protective shield underneath, also known as the jellyfish. Once we are through re-entry, the engines are shut down again and the booster goes into freefall. This is where steering becomes very important. One extra item that you'll find on every reusable rocket is a set of aerodynamic grid fins. These are able to redirect air as it flows over the booster. That allows them to steer the rocket all the way down through the atmosphere. This steering is all done autonomously. There is no person flying the rocket back down. It's a flight computer that's guided by something called an inertial navigation system, which uses sensors on the rocket to determine its position and orientation. Then it combines that information with the Global Positioning System, or GPS, to see exactly where the rocket is in the air. Then that location is checked against a pre-programmed flight path, and if the computer sees any deviation from the plan, then it's able to use all of this data to steer itself back on course. In the final moments before landing, that single engine is going to relight to begin slowing the booster down. And as the velocity drops, so will the engine's throttle setting until it's down at the lowest power level. Then, landing gear is deployed, 3 legs made from a combination of aluminum and carbon fiber are pushed out by decompressed helium gas and locked into position. Now, all that needs to be done is steer the rocket onto the landing pad and shut down the engine at the moment the landing gear touches the ground. SpaceX may be the king of reusable rockets, but regardless of who builds these new rockets, the fundamentals of reusability remain the same. As radical as the Starship Super Heavy might be, it operates on a very similar game plan to the Falcon 9. It just trades the landing legs for giant robot arms, which is a whole other video. Blue Origin's New Glenn will perform the exact same routine as Falcon 9 once it gets going. They've already attempted one landing, and the booster exploded when they tried to relight the engines, which, as we've seen, is not uncommon, but they will try again very soon. And maybe by the end of this year, we might see the Rocket Lab Neutron make its own attempt. Will it succeed? Will it explode in midair? Will it smash into the landing pad like a flaming lawn dart? We don't know, but we get to find out, and that's our favorite part of the space race.
It's quite complicated, isn't it? But you know, our engineers are pretty smart. So let's see. Sorry about that. I have to find the.
Every construction owner is saying the same.
Okay, let's talk about Starship program. The Starship program um, has been ongoing. As you know, the ISS has been up in the air for 25 years, and it's showing its age. Um, and you know, with a leak, I guess on the Russian console, which was fixed, and then there was a accident that happened in Kazakhstan, which launches the Soviet or Russian cosmonauts into space and has been out of operation. And so some of the astronauts had extra time on the ISS before they were able to get picked up. So I guess it's part of the issue with the age, and ISS is supposed to be decommissioned sometime in the 1930s. So we'll see. But so far, other than a few hiccups, things have been going pretty well. Here's a short video of the Artemis 2 rocket, which is supposed to take us to the moon again.
This is a recent animation shared by NASA showing how the Artemis 2 mission is designed to work. This mission matters because it will be the first time in more than 50 years that humans travel beyond low Earth orbit. Before astronauts can return to the moon, NASA must verify that both the rocket and the Orion spacecraft can safely operate with a crew in deep space. In the animation, the sequence begins just before liftoff. Hydrogen is burned off beneath the rocket to clear the engines, followed by the ignition of 4 RS-25 engines that release the Space Launch System from the pad. Although the rocket weighs 6 million pounds, it produces even more thrust than that. Most of the power comes from 2 massive solid rocket boosters, which provide the force needed during the most demanding phase of ascent. Once their fuel is exhausted, the boosters separate and the core stage continues pushing Orion toward space. Minutes later, the main engines shut down and Orion separates, entering free flight. Later in the mission, astronauts manually pilot the spacecraft during close approach maneuvers, demonstrating the control and precision required for future docking and lunar operations. Together, these steps make Artemis 2 a critical test, validating the systems that will carry humans back to deep space.
Quick question, George.
Go ahead.
The slide says Artemis 2 Starship moon launch.
Well, it's supposed to launch in March next month, but it's been keeping delays, so we'll see. But right now, the launch date is March sometimes.
But does the Artemis 2 involve Starship?
Well, it's supposed to be a prototype, but not going around the moon, as far as I know. But it's been a lot of hiccups. But the idea is first you launch without this astronauts and having going around the moon and come back, and then finally get the astronauts to go. This one will have the astronauts, so we'll see what happens. And I tried to find what the latest was, and it's still saying March 2026. So we'll see.
George,
It's only, yeah,
the latest I heard about Artemis 2 is, well, one is there's it's manned, but they're not landing. So they're gonna breeze by the moon surface.
yeah.
But right. And apparently they're using the same path they did in Artemis 1, which is very similar to the path that they used in Apollo 13 to slingshot around the moon to get back,
Yeah.
which is interesting. And they're targeting what you said, like spring, but I think their launch window is through like the middle of the year. So it should happen by the end of June, but I don't think they know exactly when it's going to launch yet.
Well, hopefully, if I do this next year, we can talk about it in the past tense
Well,
positively, right?
hopefully later this year we can talk about it in the past sense.
Okay.
here.
Yeah, what are they trying to accomplish by going around the moon?
See whether it's made of Swiss cheese.
It's a more efficient way of going there because you don't need to, you're using kind of the gravity. Did you see the Apollo 13 movie or you're familiar? Like when they had no engine power and they had to get the rocket home, they did this thing where they kind of slingshotted around the dark side of the moon to use gravity to kind of propel it back to Earth. So that's
The test. The test is good. We understand that. I think Jerry's asking the question of George. What's the scientific goal of the program? Is that correct? Yes. So George,
It's scientific, the objective is actually to land on the moon and then set up some kind of a space station on the moon. So it's more, I would say, engineering than science. But hopefully, once we get actually station on the moon, science will start appearing.
well, it's
But
more.
yeah, right now, I would say it's basically an engineering problem. And for those of you who remember, John Glenn was the first one that actually looped around the moon, and gave us the beautiful photos that we have of Earth looking for the moon. But that was a loop around the moon.
I believe the ultimate goal is to use the moon as a staging to launch to Mars. I think that's
Correct.
what Artemis is about. If you've ever
Yes.
watched this show on Apple TV called For All Mankind, um, it really does kind of telegraph, loosely speaking, what they're trying to do here, um, which is interesting.
Yeah, no question. I think the moon is just the first step to Mars. So, I mean, there are a lot of issues that have to be solved to going to the Mars, but getting to the moon is probably the first step. So,
George, two things, please. I think there's some grumbling here that John Glenn may not have been on that flight. It may have been somebody else, but that's just a moot point. The other thing that I wanted to ask is I read somewhere that there were problems with the heat shield on the orbiter for reentry, and that they said it was going to be, yeah, it's fine, but it's good enough. And I'm just worried about how real that is, or if you know anything more about that particular issue.
they unlike in the past where we had Apollo, uh, this is now in the hands of several commercial companies. Our Ariane is in one company, and I think the rockets are SpaceX, but the Ariane is in the Blue Virgin. So it'd be interesting to see how these companies coordinate with one another, um, because they're competing in some ways, but they're also have to coordinate. Otherwise, the whole thing's gonna collapse. So, well, it's a business slash engineering problems that have to be solved. There's very little science.
Right. Let's hope that it's engineering/business, not business/engineering.
Correct. Yes, I agree with you.
I'm clear.
Okay. All right. Going on. I guess we talked about the different ISS problems, issues, and we'll see what happens in the future. Um, Blue Origin, no, Axion, which is the third company, is trying to put together a program for a space station to follow on ISS. And so we'll see how that goes. But right now, I think ISS is on its last legs.
When's
So
it come down, the ISS?
the International Space Station.
When is it scheduled to come down?
I heard something like 2035,
10 more years?
10 years.
Okay.
But the Russians said they are going to pull out. And, quite frankly, the space station is showing its age. So I think they will, if we have a commercial space station, ISS will come down. It's expensive to, continue funding it. So anyway, let's continue. Artemis, just give you a little bit of a timeline. November 16, 2022, it uh, was beginning, and that was the Artemis 1. And we got that through all right. Then March 2026 is Artemis 2, and as we talked about it, it's right now scheduled for next month. Whether it will happen or not, we don't know. It's a 10-day mission, and the 4 astronauts are ready to go. So we'll see what happens. By 2028, Artemis 3 is the first crewed landing of the Artemis era. Now, this will be the first, if all goes well with going a loop around. NASA previously said mid 2027, but right now it's pushed to 2028. Conceptually, it's the Orion delivers the crew, as I said, and it has to match up with the SpaceX rocket. So there's a lot of coordination that has to take place. And Artemis 4 cruise mission to the Gateway in lunar orbit. And this is the beginning of building some kind of a spaceport on the moon. So be lots of things happening, whether they happen on schedule or not, we'll see.
So
Okay.
the spaceport's going to be a terrestrial configuration on the surface of the moon?
Yes. Yeah.
Well, he's saying terrestrial.
Yeah.
You mean surface of the
But
moon.
it's also going to be the launch pad for the Mars mission. So I don't think yeah, a lot of things have to be worked out yet because obviously there are issues, like for example, engine, what kind of an engine, and we'll talk about it later in this talk, that you probably want to have nuclear engines going to Mars to shorten the trip. So anyway, let's robotic space missions. We've had a number of them planned and are in there. Mars Escapade, which is a NASA mission on Mars, Spirit, and a lot of things happening, and we'll have the space launch video shortly. Okay, this is Escapade. It's a short video.
Mars, once a warm, watery world with a thick atmosphere. Now, a cold, arid landscape with its atmosphere thinned out. What caused this transformation? Over billions of years, a relentless flow of particles from the sun, the solar wind, has slowly stripped away the Martian atmosphere, causing surface water to evaporate. But how exactly did this happen, and how could it affect future Mars explorers? NASA's new Escapade mission aims to find out. The Escape and Plasma Acceleration and Dynamics Explorers mission is studying the planet's real-time response to the solar wind, helping us understand Mars's climate history using 2 spacecraft in orbit for the first time.
Past missions that we've sent to Mars to understand the interaction of the solar wind with the planet have only been single spacecraft missions. So Escapade gives us what you might call a stereo perspective, 2 different vantage points simultaneously. This will allow us to really make measurements we've never made before and to characterize the system in a way we couldn't characterize it before.
Escapade's twin spacecraft fly in 2 different formations to see how Mars responds to the solar wind in both time and space.
This is the first time that 2 or more spacecraft have worked out a formation in orbit about another planet, in this case Mars.
In the first formation, nicknamed the String of Pearls, the 2 spacecraft chase each other in nearly identical, highly elongated orbits. This allows Escapade to observe rapid changes in the Martian atmosphere caused by sudden variations in the solar wind.
When we have 2 spacecraft crossing those regions in quick succession, we can monitor how those regions vary on timescales as short as 2 minutes up to 30 minutes. Before we had to wait for 4, 5, 6, 7, 8 hours.
In the second formation, the spacecraft have different orbits that are more separated from each other, allowing Escapade to study both the solar wind and the upper atmosphere of Mars simultaneously for the very first time.
We'll have 1 spacecraft in the solar wind so we can measure what's coming in, and then 1 spacecraft closer to Mars. This will help us understand the cause and effect of what's happening when space weather comes to Mars.
Escapade will not only fill gaps in the story of how Mars's atmosphere changed, it will also help us prepare to send human explorers to the Red Planet. For example, Escapade will give scientists more details about Mars's ionosphere, a part of the upper atmosphere that future astronauts will rely on to send radio and navigation signals around the planet.
Understanding how that ionosphere varies will be a really important part of understanding how to correct the distortions in those radio signals that we will need to communicate with each other and to navigate on Mars.
Escapade's work could also help keep future Mars explorers safe.
Atmospheres can provide a shield that protect humans and other assets on the surface from things like solar radiation or intergalactic radiation. So it's important for us to understand how the atmosphere is changing in order for us to know what we have to do to protect humans and other assets we might put on the surface.
In addition to new science, Escapade is pioneering a new way to reach Mars. Previously, spacecraft launching to the Red Planet had to wait years for Earth and Mars to line up. However, Escapade is launching into a unique orbit that loops around a region in space known as L2, roughly 1 million miles away. Then, it'll return and use Earth's gravity to slingshot itself to Mars. This allows Escapade to launch early and wait in space until the 2 planets are in the right positions. This first-of-its-kind orbit will also make Escapade the only spacecraft to ever pass through a distant part of Earth's magnetotail, before beginning its 10-month cruise to Mars and starting its cutting-edge work there.
NASA's heliophysics fleet is looking at the sun's influence, and with Escapade, we'll now have multi-point measurements at Mars, which will help us have a more comprehensive picture of what's happening throughout the solar system. We need a solar system-wide understanding of space weather in order to protect our technology and our astronauts wherever they go.
SphereX is looking at the sky and trying to map it. And what we see here is the Milky Way. near infrared. Beautiful.
George, that was oscillating between visual and infrared?
Say that again.
The video was oscillating between visual light and infrared. Is that why we saw the color differences?
Yeah. Yes. And it's 360 degrees. So this is, first telescope in near infrared and what it was measuring. So,
cool.
Okay, let's talk a little bit about the commercial stuff. SpaceX, Elon Musk is probably the one that we know the most of, certainly a lot of publicity. And the Blue Origin, which is Jeff Bezos' baby, is a little bit behind, but it's they're competing with SpaceX. And then, as I mentioned, the third one is Axiom Space, and this was founded by Cam Schafferin and Michael Ciffredini, and their goal is to build a commercial space station to replace the ISS. They're probably behind, but they're funded. I mean, each one of these programs is well funded by commercial interests as well as the government. And looking ahead, one of the important things to note is that in order to go to Mars right now, it takes like every 2 years, and it takes 10 months to get there, which is, kind of hard on the astronauts. And so one of the ways to shorten the trip is to have nuclear power pushing the rocket while in transit. Right now, what happens, of course, is you get off the ground and then you float essentially for 10 months before you reach Mars. With nuclear power, you can accelerate part of the trip and then decelerate. So nuclear propulsion has been talked about for, I would say, quite a few years. But last year, NASA put out a RFP, request for proposals, and MIT successfully got one of the contracts or grants, and they're working on it. So I think probably within the next year or so, we might get somebody from MIT to talk more about it. But here is the ideas right now of how nuclear propulsion can work.
NASA is inviting proposals from private industry for a 100 kilowatt nuclear fission reactor to power operations on the Moon. With nuclear reactors now under active development for use off-world, the next obvious question is, can we use a nuclear reactor for propulsion? The answer is yes. So in this video, I will explore the idea of using a nuclear reactor to power fast transits to Mars and the outer solar system. There are two main types of nuclear transportation in the literature. First, NTP or nuclear thermal propulsion, and second, NEP or nuclear electric propulsion. We'll cover both types in the video, including the advantages of using nuclear for transportation, along with some of the challenges. Then we'll cover why propulsion follows power. That is, it makes sense to build off-world nuclear reactors for power first, before designing them for transportation. Nuclear thermal propulsion, or NTP. In simple terms, a nuclear thermal propulsion rocket, or NTP for short, works by using a nuclear reactor to superheat a lightweight fuel, usually liquid hydrogen. This heat turns the liquid into a high-pressure gas, which then expands rapidly and shoots out through a nozzle at the back of the engine, creating powerful thrust to propel the spacecraft forward. You can think of it as similar to boiling a kettle, just on a larger scale. Instead of a flame or electric element providing the heat, a nuclear reactor is used instead. Unlike a chemical rocket, which burns fuel with oxygen, NTP relies solely on heat, requiring no combustion or oxidizer. NTP engines are about twice as efficient as the best chemical rockets, achieving similar thrust levels while using only 40 to 50% of the spacecraft's mass for propellant, compared to 80 to 90% for chemical systems. This efficiency halves the fuel load or doubles the thrust duration, enabling higher velocities and leaving room for larger payloads, such as scientific instruments or crew habitats. Unlike nuclear electric propulsion, NTP provides high thrust, allowing rapid departures from Earth orbit, crucial for crewed missions. This efficiency also permits launches outside narrow planetary alignment windows, making NTP ideal for outer solar system missions to destinations like Europa or Titan, where robust habitats or landers could be transported, tasks impractical with chemical propulsion. Faster transits reduce crew exposure to radiation and other risks, requiring fewer consumables and allowing more payload for science or technology. NASA aims to limit Mars round trips to 2 years or less to minimize radiation exposure, making NTP a promising solution for efficient, high-thrust space exploration. Nuclear electric propulsion, or NEP. Nuclear electric propulsion, on the other hand, uses a nuclear reactor to generate electricity. Thrust can be generated by adding ion thrusters, scaled up to higher power levels to make use of all the electric power generated by the nuclear reactor. Typically, this will be inert gas such as xenon or krypton. Ionized particles are accelerated to enormous speeds to generate thrust, resulting in highly efficient propulsion, with the side benefit of large amounts of electrical power being available to power the ship's systems and scientific equipment. Unlike chemical thrusters that delivers quick, powerful bursts of thrust, a nuclear electric propulsion engine provides gentler but continuous thrust over a long period of time. This type of nuclear propulsion is well suited for robotic exploration of the outer solar system, as the abundant onboard electrical power can operate a large number of sophisticated scientific equipment, perhaps including active scanning systems such as radar, which typically are too power hungry for existing robotic missions. NEP is best suited for non-crewed missions due to the low thrust, which results in longer transit times. The proposed gateway station that will orbit the Moon will have powerful ion engines for station keeping. These engines could easily be adapted to use a nuclear engine for providing electric power rather than solar panels. L3Harris is working on the power and propulsion system for the gateway station. Their ion thrusters operate at 12 kilowatts and are the most powerful electric propulsion system ever developed. An L3Harris spokesperson said, "For a nuclear electric propulsion system, we don't need to change the reactor or the power conversion system. We just need to optimize the radiators to reject heat into space and put electric propulsion systems on the other end." Unquote. Nuclear power eliminates the need for large solar arrays, which reduces the mass of the system.
As I said, MIT is working on it. Somebody, who has contact with MIT should try to follow, and maybe we can get a talk sometime later this year, because it sounds very interesting. There are a lot of challenges that come along with a nuclear engine, and that is shielding, radiation shielding of the crew. For unmanned units, it's a perfect thing, but for man, there are issues that need to be solved. Okay? Any
George,
questions?
send me a note and I'll try to see what I can figure out, get somebody to figure it out.
Okay, great. All right, well, the last part of this is kind of it's a 3-hour video, which we only will listen for about half an hour due to time constraints. But anybody who's interested, I suggest you watch the whole thing sometime in the evening with a glass of beer or a little cocktail and watch. Anyway,
George,
yes?
We're talking about the nuclear engines. correct me if I'm wrong, the Voyager has a nuclear engine, correct? Or they have nuclear engines?
Well, we've had nuclear. I mean, if you call them nuclear engines, the Voyager has plutonium engine, which powers it, and but I don't know. I don't think that would be classified as a nuclear engine because all it is source of radiation, which gives you heat and then convert it to power. But we've used nuclear materials for powering long distance missions. But this is a engine, so it's a different cattle altogether. And there's a separate video on problems with nuclear engines in space with crewed capsules. But that's we can wait with that when we hear progress being made.
So George, they
Yes.
talked about reducing the transit time from if it's not powered in flight. So what kind of speeds are these rockets delivering?
It will cut the transit time to Mars in half.
So what's the speed that these are going at?
Well, as I said, time-wise, it will cut it in half. So instead of transit of like 10 months, this will be able to get 4 or 5 months transit, which it's an important part of cutting back because radiation from a long exposure trips is something that people don't really understand yet very well.
So is this like 10 kilometers per hour, 10,000 kilometers per hour?
Well, I think,
or is it, what range is that in?
We can think a little bit.
Yeah,
hour, about 22,000 miles an hour. Go in orbit. So this is escaping the Earth's gravity, so it's going a little faster than that. So let's
got an average too, because it's not going to be constant the whole time.
So let's pick a number and say 50,000 miles an hour, right? And so these are cutting it in half. It's going to go like 100,000 miles an hour.
32,000 to 48,000 kilometers per hour, which is 20,000 to 30,000.
Let's pick some units, guys.
So it's faster than you and I can run.
20,000 to 30,000.
Let's put in the upper
like
limit
NASA
on
or something.
well, but
the acceleration.
speed is relative to what? Relative to Earth, relative to Mars. So all you can really talk about is time-wise and acceleration, because that's something in absolute.
Yeah.
What's the upper limit on the acceleration?
Light.
Okay.
Although
It's not getting anywhere close to the speed of light.
Oh, no. It's far from speed of light. Very far.
Yeah.
I mean, it takes to Mars, is it like 8 minutes? Or no, it's 30 minutes. 30, well, it depends upon how far Mars is from Earth, but it's somewhere around 20, 30 minutes of one way, speed of light.
So, you could commute if you had to.
Yeah, you can compute it.
I'm wondering on the nuclear power, what its practical limit is on the transit, the speed. Does it just keep accelerating, or is it some hit a wall?
I think what happens is it keeps accelerating, then it starts to decelerate, because remember, once you get up to a certain speed relative to your to Mars, you need to decelerate it. So it works. You accelerate and then you have to decelerate. So
they're rockets too. So you have to carry that mass that you're going to shoot out the other direction with you. So you have to accelerate that on the way there. So
Yeah.
so you're kind of mass limited. There's a specific
You know,
associated with these engines.
I don't know if you accelerate halfway and then you decelerate the other halfway. So,
But even having
I don't-
nuclear doesn't
Yeah.
take
No, you need
having to
matter
carry
to,
that mass
to
with
be
you.
ejected, right? Yeah.
The corollary is real simple. It's not the long fall, it's the sudden stop.
anyway, I think we need to have a whole talk on it to get more of the details. Okay. So here's the first part of it is quite interesting because it talks about the findings from the Cassini mission, which you remember was going around Saturn and its moons. And one of the moons is really particularly interesting because of what's happening on it. So here it is.
Iapetus, Saturn's mysterious moon, is slowly drifting into the giant planet's shimmering rings, moving at a speed of about 3.2 kilometers per second. And according to research from the Cassini spacecraft, this process may take millions of years to complete. Yet the effects it is already creating are producing changes in the ring system that are almost beyond imagination. Dust trails, fragments, and strange materials are being expelled, forcing scientists to confront urgent questions. Could Iapetus eventually become part of Saturn's rings? Or will this collision open a new era in our understanding of the universe? The mysteries surrounding Iapetus not only capture scientific attention, but also challenge our current knowledge of how the cosmos works. And the strange, paradoxical journey it is undertaking may hold the key to unlocking some of Saturn's deepest secrets. A silent yet powerful process has been unfolding for billions of years. A collision that produces no explosion, no violent shattering, but is persistent enough to reshape the ultimate fate of this moon. Its slowness and endurance are what make it so formidable. A mechanism unlike any type of impact humans usually imagine. And to understand it, we must step away from Iapetus's surface and look outward, toward a much smaller moon playing the central role, Phoebe. Phoebe orbits Saturn in a retrograde direction, a signature trait of a captured object, possibly originating from far beyond, perhaps from a region as distant as the Kuiper Belt. Its composition is rich in carbon, dark, cold, and fragile. For billions of years, impacts from micrometeorites have blasted countless dust particles from its surface. And over time, those particles did not disperse. Instead, they formed an enormous structure, the Phoebe Ring, the largest dust ring around Saturn, stretching from about 6 million kilometers to more than 12 million kilometers. Despite its extremely low density, its sheer size makes the total amount of dust substantial enough to influence any body passing through it. Iapetus orbits right inside the region swept by the Phoebe ring. But the dust does not simply fall onto Iapetus by itself. It needs an invisible push, and that push is solar radiation. Photons streaming through the dust ring, colliding with each grain and producing a slow drag known as the Poynting-Robertson effect. As this force continuously acts on the dust, it loses orbital energy and slowly spirals inward. Meanwhile, Iapetus orbits Saturn in the prograde direction, while dust from Phoebe moves retrograde, creating a very high relative velocity between them. Thus, every speck of dust, tiny and light as soot, strikes the leading hemisphere of Iapetus with enough energy to disrupt its microstructure and adhere to the surface. The effect is similar to a car speeding through the night. The windshield collects every insect in its path. On a cosmic scale, Iapetus is that windshield. A moon forced to plow through Phoebe's retrograde dust stream on every long orbit. The strongest evidence for this mechanism was recorded by the Cassini spacecraft during its close flyby of Iapetus in 2007. It detected a dark coating only a few centimeters to 1 meter thick, far too thin to be produced by any internal geological activity. Impact craters exposing bright, pristine ice beneath the surface made it clear the dark layer is not native bedrock, but a coating. A shell accumulated from the outside, particle by particle, molecule by molecule, over billions of years. Remarkably, orbital models from 2023-2024 precisely simulated Iapetus's current path through the Phoebe ring. And the results showed that its leading hemisphere lies exactly in the region of highest dust concentration. Meaning, Iapetus's orientation and rotation make it the perfect target for this incoming stream. But this collusion mechanism does not end with dust simply coating the surface. As the dark layer grows, it absorbs more sunlight, causing the darkened regions to heat up and trigger sublimation of the ice beneath. If this process continues for billions more years, models from 2024 predict that an average of 100 meters of surface ice could disappear every billion years. A tiny number on human scales, yet monumental when compared to the age of the solar system. This leads to a profound philosophical consequence. Cosmic collisions are not always explosive events. Sometimes the most transformative forces come from the gentlest touches. The quiet grains of dust without sound or light, which, when given time, become powerful enough to reshape a world. So, could Iapetus eventually disappear? Over time, its surface ice may erode, its structure may gradually weaken. And in the distant future, material stripped from Iapetus may become part of Saturn's ring system. As we move closer to Iapetus, we step into a paradox, a moon split in half by two opposing colors so extreme they appear as though they belong to entirely different worlds. The dark region, Cassini Regio, named after Giovanni Cassini, covers nearly 40% of the surface. With an albedo of only 0.03 to 0.05, equivalent to a tar-coated landscape. Every photon of sunlight that falls onto it seems to vanish without return. In contrast, the bright hemisphere reflects light with an albedo of 0.5 to 0.6. Nearly as bright as Enceladus, one of the most reflective bodies in the solar system. The two halves of this moon differ so drastically that if you place them side by side without context, you might easily believe they came from two separate worlds. On most moons, materials mix. Heat causes sublimation. Ice migrates, and solar wind erodes. Everything blurs the surface into gradual transitions of texture and color. But Iapetus breaks this rule. Its boundary between dark and light shows no transition from gray to shadow. Or from white to pale. Instead, it is a sudden, abrupt leap from bright ice to pitch black dust. Spectral data from the Cassini spacecraft, reanalyzed in 2023, revealed that the dark region contains high concentrations of carbon. Complex organic compounds, such as PAHs, and spectral signatures matching dust from the Phoebe ring, the massive dust structure surrounding Saturn and sourced from the retrograde moon Phoebe. This confirms that the dark coating is not native to Iapetus, it is an external layer. Yet this is only the surface of the mystery. The layer is astonishingly thin, measuring only a few centimeters to about 1 meter. The interplay of heat, ice, and time creates a cycle so slow it cannot be observed within a human lifespan. Because Iapetus rotates once every 79.3 days, one side faces the sun for extended periods. And it is precisely this Cassini region that absorbs the most solar heat. As the dark surface warms, the ice beneath begins to sublimate, releasing thin vapor from a world nearly motionless in every other sense. As the ice disappears, the dark dust becomes even more exposed, increasing absorption and driving the region into a self-amplifying thermal loop. This feedback cycle is what allows Cassini Regio to remain a deep, persistent shadow, sustaining itself over billions of years. Meanwhile, the sublimated vapor does not vanish. It migrates to the colder, bright hemisphere. There, the vapor freezes and accumulates as fresh layers of white ice, enhancing its powerful reflectivity. This implies a profound truth. The brilliant side of Iapetus was not gifted at birth. It was built slowly, molecule by molecule, over billions of years as drifting vapor settled into the cold. Physically, this means the bright hemisphere continues to brighten with time, while the dark hemisphere sinks deeper into blackness. Thermal model simulations published in 2022 showed that Iapetus possesses the strongest feedback cycle ever recorded on any body in the solar system. Here, light and darkness are not mere surface states. They are the results of an ancient battle between energy and matter, between heat and ice, between accumulation and erosion. What is astonishing is that this entire process unfolds in near silence. No violent collisions, no shattering ice cliffs, no volcanic eruptions. Only dust, sunlight, and time. Three subtle forces which, when woven together, create one of the most spectacular phenomena in any planetary system. However, this thermal feedback loop is only part of Iapetus's transformation. Because lying directly at the intersection of this stark light-dark divide is a geological structure science has yet to fully explain. An equatorial mountain range rising nearly 20 kilometers high, positioned absurdly precisely along the equator, stretching more than 1,600 kilometers. Between darkness and light, between the invisible cycles of erosion that span billions of years. Iapetus carries a signature so unusual that even NASA describes it as unlike anything we've ever seen in the solar system. A colossal equatorial mountain range stretching across nearly the entire circumference of the Moon. Standing upright like an ancient wall, dividing a world already split in two. No moon of Jupiter, no satellite of Uranus or Neptune. Not even the distant icy bodies of the outer solar system possess anything remotely comparable. Only Iapetus holds this giant spine, a wonder Cassini observed up close in 2007. instantly recognizing it as a story that did not belong to any familiar orbit or ordinary geological process. The ridge spans 1,600 kilometers, is roughly 200 kilometers wide, and rises in some places to nearly 20 kilometers, taller than Everest in absolute height. What confounds scientists even more is its absurdly perfect placement. The ridge sits exactly along the equator, not even a single degree off. Precision nature rarely produces unless shaped by extraordinary events dating back to the earliest days of the solar system. There is no surface tectonics, no internal compression, no magma pushing upward from below. So what could raise a frozen wall thousands of kilometers long? Scientists propose two major hypotheses, and though they differ in mechanism, both lead to the same conclusion. The ridge is one of the oldest surviving features of Iapetus, possibly dating back more than 4 billion years. According to the traditional hypothesis, early Iapetus may have rotated far faster than it does today. Perhaps with a 16-hour day rather than the current 79.3 days. With such rapid rotation, centrifugal force would have been strongest at the equator, pushing outward on the moon's soft, mostly icy crust. If Iapetus' surface was still partially molten or weak at the time, its materials would not resist the outward pull. The moon would bulge like a fast-spinning sphere, forming a dense equatorial band. Later, as tidal interactions with Saturn slowed its rotation, the surface cooled and froze into the stretched shape, leaving behind a solidified ridge of ice. This model explains the ridge's great length, the walnut-shaped outline of Iapetus, and the similarity between ridge material and surrounding terrain. But how does a soft early structure preserve a height of 20 kilometers once frozen? And why would the bulge manifest as a sharply defined wall rather than a broad equatorial swell like those seen on fast rotating planets? These questions make the second hypothesis more compelling. In this scenario, a small moon of Iapetus or another icy body may have been torn apart by tidal forces, forming a miniature ring system around the moon, similar to Saturn's but vastly smaller. If this ring lay within Iapetus's Roche limit, its fragments could never reassemble into a new moon. Over time, orbital drag and interactions with the icy surface would cause the ring to collapse inward. Every fragment would fall in only one possible place, the equator. Modeling from 2024 shows that the height, width, and sharpness of the ridge align almost perfectly with the ring collapse scenario, a process that may have taken tens of millions of years. If this hypothesis is correct, then Iapetus once carried a ring of its own, and the equatorial ridge is not merely a physical remnant, it is historical evidence. It preserves traces of ancient rapid rotation, the aftermath of a massive collision, the imprint of orbital instability, and possibly even the ghost of a moon that no longer exists. With no tectonic activity to erase it, no rain or wind to erode it, the ridge has survived nearly unchanged for billions of years. It stands there still, not only dividing the moon's surface, but dividing its history. Before and after Iapetus settled into the cold, still form we see today. Under Iapetus's conditions, ice at extremely low temperatures becomes incredibly strong, almost rock-like, and at around minus 143 degrees Celsius. Icy material can bear long-term stress without deforming. And without meaningful internal heat or periodic warming, the structure has preserved its shape for eons. The ridge endures because Iapetus is a world of absolute cold and absolute silence. Two perfect conditions for time to turn everything into stone. The equatorial ridge is not only Iapetus's greatest mystery, it is the key to understanding the moon's entire geological and orbital evolution. But the story does not end here, because this colossal wonder is also caught in the same slow cosmic erosion that is steadily reshaping the entire moon. At the heart of this thermal feedback loop lies a simple yet profoundly consequential fact. Iapetus has a day that lasts 79.3 Earth days. This forces every point on its surface to face sunlight for an unusually long stretch of time. There is no rapid day-night cycle like on Earth, no mechanism for quick cooling, no winds or atmosphere to redistribute heat. So once any region absorbs sunlight, it retains that heat long enough for irreversible changes to unfold. At Cassini Regio, the dark hemisphere, the extremely low albedo of 0.03 to 0.05 means sunlight is almost entirely swallowed. Though the total heat gained is still modest by Earth's standards, the surface remains tens of degrees below zero. But because water ice is the primary material composing Iapetus, even a small temperature increase is enough to trigger sublimation. Remarkably, the carbon-rich dust coating the dark region is only a few centimeters to at most 1 meter thick, according to Cassini's 2007 data. The ice beneath this dusty veneer is easily exposed to sunlight. As the ice sublimates, more dust is left behind, the dark layer grows thicker, and that means it absorbs even more heat. A 2022 thermal model concluded that Iapetus has the strongest thermal feedback loop ever recorded in the solar system. No planet, moon, or asteroid exhibits a cycle as stable and long-lasting. Under Iapetus's low gravity and extremely thin surface pressure, water vapor travels easily across the terrain like a ghostly drifting gas. And when it reaches the colder region, the bright hemisphere, it recondenses into fresh ice. This creates a phenomenon not observed on any other moon. Iapetus is actively transferring ice from its dark side to its bright side. If we imagine Iapetus as a living sphere, we can see it slowly shifting material from hot to cold, like a world breathing in slow motion. The recrystallization of ice on the bright hemisphere not only preserves its brightness, but steadily boosts its reflectivity over time. With an albedo of 0.5 to 0.6. The bright hemisphere functions like a massive ice mirror, bouncing away most of the sunlight and keeping the surface so cold that sublimation almost never occurs there. Thus, while the dark hemisphere gradually loses ice, the bright hemisphere is continuously replenished. A natural polarity maintained by the fundamental physics of ice, light, and vapor. Even more astonishing is that this feedback loop not only shapes color and reflectivity, it directly alters Iapetus's terrain. As ice sublimates, the surface becomes more porous and weaker, easier for dust to settle on, and more vulnerable to deformation from even small meteoroid impacts. The bright hemisphere behaves in the opposite way, more rigid, more stable, becoming a cold reservoir that stores the moon's redistributed ice. Philosophically, this reveals that polarization is not just a surface effect, it becomes a transformative force that reshapes the material structure beneath. The feedback loop is rewriting the face of Iapetus. Not with magma, not with quakes, but with light, shadow, and time itself. Through the Voyager and Cassini missions, a slow and unsettling truth emerged. This is not a typical moon of Saturn. But an object that defies every familiar logic of how icy bodies form and evolve. First, consider the density of Iapetus. Only about 1.2 grams per cubic centimeter, significantly lower than Titan, Rhea, or Dione. This value reveals that roughly 75% of Iapetus is water ice, with the rest composed of light rocky material. There is no evidence that internal heating ever melted or differentiated its layers, meaning Iapetus has remained nearly unchanged since the moment it formed more than 4 billion years ago. Its shape deepens the mystery even further. When spacecraft captured global images of Iapetus, it appeared like a giant walnut, bulging dramatically at the equator. Such a figure can only form if, in the distant past, Iapetus once spun at incredible speed. Dynamic models suggest it may have rotated once every 16 hours, before tidal forces from Saturn slowed it to its present 79.3-day period. While Iapetus was still warm enough to be slightly malleable, its rapid spin would have caused the equator to swell outward once the surface cooled. That shape froze permanently into place. This is evidence that Iapetus underwent a formation history entirely unlike the other major moons of its era. But while its shape may be strange, its surface is even stranger. The density of impact craters, ranging from hundreds of kilometers across to innumerable tiny pits, reveals that Iapetus's terrain is profoundly ancient. Some regions may be 4 to 4.3 billion years old, nearly matching the age of the solar system itself. This is a world locked in stillness, one that has experienced virtually no geological activity for billions of years. No cryovolcanoes, no resurfacing, no internal flows. And then there is its orbit, at 3.56 million kilometers from Saturn. Nearly 3 times farther out than Titan, Iapetus sits beyond the strong influence of Saturn's magnetosphere and particle belts. This isolation makes it feel detached from the dynamic system that shapes the other moons. like a solitary fragment drifting on its own. Its orbital inclination, a steep 15 degrees relative to Saturn's equatorial plane, reinforces that idea. According to a 2023 analysis by JPL, this unusual tilt may signal that Iapetus was captured during the early solar system. This implies Iapetus may have formed elsewhere, perhaps in a region where small icy bodies were being scattered by intense gravitational interactions. Then, during the chaotic era of planetary migration.
So only a couple more minutes before the end, but I understand that it's 10 minutes after 11:30, so I'm consistent. But let me run it to the end, and then we can end the assessment.
The period referenced by the NICE model, Iapetus was swept into Saturn's orbit and gradually settled into position. A world composed of 75% ice, without a clearly layered core, shaped like a spun-out object frozen mid-motion, carrying a surface almost as old as the solar system itself, and orbiting at a tilt so severe it seems as if it never truly belonged to Saturn. All of it forms a paradox. Iapetus behaves like a primordial ancient moon, yet it bears scars of dynamic forces from elsewhere. And from this long-standing strangeness, a phenomenon unlike anything else in the solar system emerged. The most extreme bright deck dichotomy known. It is not a temporary shift, as Giovanni Cassini once believed, but a deep, long-term consequence of its structure, orbit, and interaction with a surrounding sea of dust. The gravitational interaction between Iapetus and Saturn's ring system is not merely an intriguing astronomical phenomenon. It is a vivid demonstration of the universe's restless, ever-shifting nature. With its unusual orbit and steep inclination, Iapetus is undergoing a collision that moves slowly, almost imperceptibly, yet progresses in a direction that cannot be reversed as it grazes the outer edge of the rings. This gradual absorption of material and the reshaping of the ring's structure stand as living evidence that even the oldest satellites are never exempt from the dynamic laws governing their cosmic surroundings. The slow orbital drift unfolding over millions of years illustrates the fragility of structures that seem unchanging when viewed on human timescales. Although this process spans geological epochs, its final outcome is unmistakable. Iapetus, a solitary frozen world, is writing the last chapter of its cosmic story by merging into the grand architecture of its parent planet. becoming a testament to the laws of change and gravitational influence that shape every piece of matter in the deep expanse of space. This story reminds us that nothing in the universe remains still. Every world is moving toward an ending shaped by gravity, time, and the slow fading of cosmic nature.
This is very interesting because Cassini ended, 10 years ago, 8 years ago, and here today, we're finding results that are still extraordinarily interesting. And I'm looking forward to seeing some of the other things, or the other moons that Cassini will be giving us.